Hi, I'm Shivas Jairam, and I'm going to talk about a use case of artificial neural networks in manufacturing. So, the problem I'm trying to solve is to help the supply chain planning folks in a manufacturing facility to predict product demand for the next um, days using artificial neural networks in carriers. So first, let me walk through the technology stack. So there's two types of technology involved in my project. One is for the data exploration and model building. That's what you see in the left, which consists of Anaconda as a base, Python, Jupyter notebooks, and the packages Pandas, NumPy, Matplotlib, TensorFlow, and Keras. To the right, you can see I have an end use application which consumes models which are built by the model building layer. And this is a web dashboard app with a Python backend, which had Pandas, NumPy, TensorFlow, Keras, and Flask as packages installed, and a web front end which was built on jQuery, Angular, D3, and Bootstrap. Now, a quick look at the technology architecture of how all of this would work. So at the bottom, you have the Python layer, which has our TensorFlow and Keras installed, where we can build our artificial neural networks, which can collect data, generate models, train models, evaluate, and find the best model. Now, these models, to be exposed to the outside world, we have a package called Flask, which can expose these um, calls to, for example, to Keras as a REST API, and then an Angular application could call that REST API, call a predict function on a model, get the results, and show that results back on a web dashboard. So the installation of my project consists of, again, two folds. One is the model building part, which is you download Anaconda. And then I created a separate virtual environment for this project, called it CS89 project, and installed NumPy's Pandas, Matplotlib, Flask, TensorFlow. And if you have GPU, you can install TensorFlow GPUs and Keras. Then I reused the same virtual environment for my backend of the web application, and then I installed jQuery, Angular, D3, and Bootstrap. Now, the data set for this application, I extracted it from the data warehouse from this manufacturing facility, and it consists of items and item commodities and the number of items, the quantity of items shipped on a daily basis. Now, initially, I was thinking of doing this project to predict an item demand and predict the number of items required, but the number of data points at the lowest item level was very less. So I had to kind of group up items together into commodity and then look at patterns in the commodity. So the data set consists of data from 2016 to April of 2018, and this is all for one manufacturing facility which produces cans. And I had two files, item data and the commodity data, but the primary file I use for this project is the commodity data. It's only around 300 kilobytes and it has around 8,000 rows, and you can see a snap of the data at the bottom of the slide. So the first step I did was, once I loaded the data, I explored both items and commodities individually, looked at how many unique items do I have, how many unique commodities do I have, how many unique items were shipped every year, or how many unique commodities were shipped every year. And at the bottom, you can kind of see a simple trend of the items which were shipped on a daily basis for the 2 years and 4 months of data. Now, one thing which came out of this is not every item or every commodity is shipped every day. So there are actually gaps in the data set, which, so for example, every Saturday, Sunday, you would not ship anything, so it would be zero. And then from Monday to Friday, 3 days of a week, one week you may have shipments, and then another week you may have 4 days of a week you may have shipments. To fix this, I had to prepare the data by taking the minimum and maximum dates in the data set and creating a day sequence. Like, so if you put the minimum as 1 and then you increment it for every day, and created a day sequence, pivoted the numbers to made so that I made all these days as columns, and then for missing days I added columns with null values, replaced nulls with zeros, and then pushed the pivoted data back into rows so that I had a regular time series with zeros in the days where there were no shipments. And this was important because I needed data in this format for my to be used in the next step, which is the modeling step. Now, before getting into the modeling step, one of the things I did was to use a model generator class. So it was basically a wrapper class around carers. So instead of using carers directly and building models, I created this wrapper where you can pass in parameters, and based on the parameters, the carers models get generated. So I had two subclasses, which was for the multi-layer perceptron model and the LSTM models. So if you look at how I built the MLP class, you can see most of the code is generated on the fly. So like your model layers, for example, the hidden layers are generated on the fly based on parameters. The input nodes, the amount of look back on the data, etc., all comes in as parameters. So the advantage of this is you could then when you're in your training stage, rather than start with a static model, you can set up a bunch of parameters. These parameters could be passed in to this generator class. Models could be generated, trained against the data, and then evaluated. Similarly, you can look at the LSTM. You can see how none of the model code is actually fixed. It all depends on the input parameters. So our first step in modeling was to pick up some base models. So I pick up a multi-layer perceptron model without look back, with look back in the time series, and LSTM with no look back, with time steps, and an LSTM with state. So I used these 6 models and came up with just some basic default parameters, ran it through the data set, and you can see the train, test, and some predicted results, and this gave some performance metrics, and you can see the metrics in the screen. But what this gives us is, okay, this is our base models. Now we need to make these models better, and we need to perform better than this. Now these base models was for just one of the commodity, which was nut, but we need to find models for all commodities. And as I mentioned earlier, see, you cannot use the same model for every commodity because the data set patterns for each commodity is way different, and so we need to find the right model for each commodity. So the way this auto generator tool works is you can send in a bunch of parameters. So it's kind of like a grid search you would do using scikit-learn, but here even the model gets built dynamically. So for example, in this slide, I have the input units, which is 12, 24, and 48, and that's the number of nodes in each dense layer in the input layer that can vary based on different models while these models are being generated. So it's a little bit more than just hyperparameter tuning, because you're building the models in fly, on the fly, as you're training to find the best models. So, and at the bottom, what you're seeing is you're iterating through this these combinations, creating a model, evaluating it, saving the model, and then storing the performance metric. So as a result of this, what you can see is, I set in a bunch of parameters and said for each of the commodities run these models, but I quickly ran into my models were taking too long to run, so I had to cut down on the number of models. So you can see my LSTM time step and LSTM state models, I used a very less amount of parameters, because when you see the MLPs and the LSTM basic ones, I used hundreds of models, whereas I had to bring it down because my total runtime was going over a day and I couldn't afford that much of time training on models. So even in my experiment, I had 800 models, which took over 24 hours to run, But what this gave us was, it gave us different models for different commodities. So you can see the top 5 models for the commodity nut, the top 5 models for the commodity supplement, and then at the bottom you can see the best models for each of the commodities. So what this has done is, it's taken a bunch of parameters, taken your data set, and then for each commodity runs all these different combination of models, finds the best model and brings it back to you. And it also saves these models. So what we can do with these saved models is, these top performing models can then be passed on to other applications, which can then use those models to predict and use those results elsewhere. Now this whole auto generation functionality could be run daily on new data. So as shipment data is received every day from the data warehouse, this could be fed into this auto generation model. It runs for a few hours, generate the hundreds of models. We find the best model for the commodity and move them over to the end use app, which can then predict based on that. So the planners have a fresh model every day. So the next slide, what you're seeing is where I built an end use application which could actually consume these predicted models. So what I'll do next is, I'll go for a quick demo of this application. So this is an Angular application which basically represents the same data set. You're seeing the history for the last 2 years, from 2016 and 2017 and year to date 2018. And what you see in the red line is the predicted line using the model which is selected to the right. So it is an LSTM model with a look back of 10, stacked nodes of 4, batch size 4, and a test MSE metric of 0.919. So a planner who comes into this dashboard can now say, okay, let me pick another model, and you can see how the predictions changed and your demand for the next 10 days changed. And this model is using a look back of 30 points. It has a test metric of 0.81. So, or you can pick another one where you can see the predictions again change. So what this app is showing is, you can actually consume your trained model in an end use application where actual users can use your pre-trained model to predict results and use those numbers in a real use case. So in this scenario, it's a demand dashboard. So a planner could come in and say, for my commodity nut, I would pick an LSTM model, and I can see my total demand for my manufacturing facility based on the models from different commodities, and these predicted numbers could then use for supply chain planning and other okay, so next I'll go back to the PowerPoint. Okay, so the next slide is again it's showing how we can use the trained models in an end use applications. Now these predictions which you saw was generated dynamically. So the front end app actually called the backend Python service to which actually made a prediction on the data for the next 10 days and gave it back. So this is not some data we store for the model. So this is actually happening dynamically. So if we had a use case where the front end application had user inputted data, we could actually predict that based on some parameters coming in from user input. So in summary, what we have seen is auto-generating of models and training them to find the best model for each subset of data was the best approach to find the right model for the commodity of data we're looking at. The dataset showed no real pattern in the time series, and model prediction results varied a lot based on the commodity. Now we were able to save these models and use these models in another web dashboard, which I think is really useful, or on a real use case which could be used in multiple applications. The lessons learned is the demand pattern for each commodity was different, and we have to build separate models for each commodity. Like we saw, the data set had irregular time samples with a lot of gaps, and we had to handle that before model building time. Auto-generating models was an interesting approach, as neural network models of different configuration architectures could be built and trained automatically. Now, The disadvantage of auto generation is it takes a lot of time to generate, so you have to optimize on what parameters and what model structures can be built in the auto generation step. One thing I learned was Keras was much easier to build models with rather than TensorFlow, and I would definitely need a new graphics card on my Ubuntu desktop. With that, that's my last slide, and thank you.